Go on in, everyone. So now I accidentally pinned one of my students to the screen. I don't know why. I know how, but I prefer to pretend like it was a gremlin in the machine instead of me just not paying attention and doing something stupid. Anyone have any questions while we're waiting for class to start? We have a whole minute. Man, McCullough looking rough there. What's going on? I got pushing kitty. Ooh. In fact, I'll be wearing this right now. Show you the cool cat. Yeah, that was my dancing. Awesome, man. All right, we got less than a minute. Anybody have any questions before we get started? I'm gonna go ahead and knock out the rest of chapter 3 today. Maybe even get us started a little bit on chapter 4. I'm also going to use something called the dot product, which I think you should all have some knowledge of. I mean, I've hinted to it a couple of times this semester, but having taken trig, you're supposed to cover vector. You normally cover vectors there, and quite often that includes dot products and maybe even cross products. Another name for the dot product is called the scalar product, and then there's another name for the cross product, which is called the vector product. And actually, there's more than one vector product. You can do all sorts of different things, multiply vectors in weird ways. There's a dyad product that makes tensors and crazy stuff like that. So, but so far, all you need to know is dot product, and soon enough, we'll be covering cross products. All right, we still got people coming in. So no questions. That makes me feel pretty good. Feels like I might be doing something right. Let me check something on our actual course while we're at that. I'm going to look at my modules and double check. So currently I have chapters 1, 2, 3, and 4 practice questions up. I've got practice tests 1 for 1 and 2. And in fact, the test 1 is due tomorrow. I've got to reopen that practice test, and y'all need more time to do that. Let me fix that real quick.
Thank you.
Yeah, no problem. Yeah, that was when I had the original due date, so it shouldn't be that. So y'all have until 11:59 p.m. tomorrow to complete all your attempts. You get 3 attempts, and only the highest counts. As far as the test goes, but the practice test, of course, you get all the attempts you want. Probably tomorrow morning or soon thereafter, I'll put up another practice test for test 2, and I'll probably go ahead and put up online test 2, and that's probably going to be due like maybe not the 12th, but it might be the 15th or something instead of the 19th. So just be prepared for that. I like you to have a whole week basically with the practice test, but I don't mind, since you can take it any day in that whole week period. I don't mind putting the test, a week away or 8 days away from now. Hopefully you guys have been working on your practice test. A student asked me today, chips are down, what's the best thing to study? Well, to be honest with you, I'm not sure how much you can get done in reality without reading the book enough to, or at least the examples within the book enough to actually do the online homework, unless you're just using Chegg for everything or something like that. I gotta tell you that using Chegg makes you feel like you really are learning this stuff, but you're really not learning this stuff unless you're solving problems on your own, beating your head against the wall, trying this, trying that, and that sort of thing. it's perfectly fine. I want you to use Chegg as much as you can to make sure you get right answers so you can make good grades on your homework. But it can become too much of a crutch. So really what I would advise my students to do is, one, if you can't read the whole book, which I really think you should, in fact, ideally you would read it 3 times in a given semester. But ideally what you want to read is enough of the actual example that you can work out the example. If it doesn't make sense when you're reading the example, then you might have to read a paragraph or 2 before that, and then the next example, and then the next example, and then the next example for each chapter. And then hopefully you can, maybe with looking up 1 or 2 for help, you might be able to do the homework. And the best way, again, of looking it up is looking it up, seeing how you think they did it, close up that Chegg or whatever you're using, and then try to solve the problem again. Again, if you run into a hard spot, open up Chegg again, look and see if you did anything wrong. If it's just a matter of you don't know where to go next, maybe Chegg will be nice and helpful. You might even need to just restart again with Chegg closed and try it over. And then from there on out, I really just focus on taking the practice test, because the practice test, the more times you take that, and it's not uncommon for my students to take it 25, 30 times on every practice test. But if you get to a point where you can take 3 of those in a row and score an 80 or higher without looking anything up, then you probably are in a pretty good spot. If you can't do it 3 times in a row without looking stuff up and without making an 80 or higher, then yeah, you probably have learned really well how to look up stuff, and that's not what we're shooting for here. This will, I promise, guys, this will come back and bite you if you become an engineer or a scientist, not knowing some of these topics, even when they seem somewhat unrelated. For instance, in mechanical engineering or something like that, it will come back and bite you. So, no questions. Let's go ahead and solve some. Yes,
Professor. It's kind of hard for us to want to like bash our heads against the wall to do these questions when my lab takes off points for every time we make an attempt.
Right.
And then I lose points. So if I bash my head to the wall and I do the conceptual, but then I finish the thing, it's like, great, I learned everything, but I got a 50 on my homework.
I would say trust Mr. Younger in the sense that my syllabus is the worst thing I can do to you legally. Okay. And that's the way it is every semester. And if I look and I'm seeing this student that's really working their butt off, but making bad homework grades, but somehow managing to make good, not only good online tests, but specifically a good midterm exam, then I don't care so much about what's happening in those homeworks. Okay. Now, if I see zeros on the homeworks, that means you're not doing them. Now, no life rope goes out for that. But when I see people with a bad homework grade, and a bad homework grade is, a series of 60s and 70s and stuff like that, where, and it tells me, it gives me a full report on how much you spend on each question, how much of the time is, idle, and like your computer went to sleep. It can tell me that kind of stuff. So if I'm seeing that kind of junk, then I can tell that you just walked away versus you're really trying to work problems. If I see that kind of profile, then I'm very, very likely to look at your grades and see what I can do to make them better. And I do that every semester, and I do that for every student. The whole purpose of the homeworks and the whole purpose of the practice tests are so that you can do really well on all the tests, but most specifically the midterm and the final, because the midterm and the final are the ones that are absolutely proctored and taken by the person whose photo ID has been shown and whose photo ID matches the person enrolled. But yeah, you make a good point. It's exactly right. I do want you to do that, but like I said, I want you to make good grades. And I don't know why my hat can't stay crooked straight. It gets worse every time. But anyways, and I do want you to make good grades. But I tell you, the most important thing for you to make good grades on is that proctored midterm and that proctored final, which again, proctor could mean you go into the testing center and have it proctored. Our proctor could mean you're going to have Respondus lockdown browser along with Respondus monitor watching you. And by the way, I set it up where I can come in at any time while you're taking the test as well and look at yours, your camera as well. So just don't do something that makes me have to conclude or give you an F for a test. That would be bad. If my choices, if I had my choice, I would give all of those tests proctored and online. But I know it's kind of a pain in the butt. But I do want a full, nearly 50% of the course grade is going to come from those two tests where you don't have access to the internet and books and notes. All you have is your equation sheet. Anything else? But you did bring up a good point, and I just wanted to let you know, if you look, or at least the last time students have told me about how I rate on whatever websites or whatever, a lot of people say I'm hard and a lot of people say I'm fair, and that's what I'm shooting for. Is I want to teach a course that's exactly the rigor that you would have if you were at UVA, Virginia Tech, Duke, or Princeton, Harvard, Yale. I want this course to be every bit as rigorous, but at the same time, I also want this course to be way more fair than you would get in a typical class. Like if you took this class at Chapel Hill, you'd be in a room of 450 students. So I have the capacity to, by only having 24 students or so, I can one by one come grade time look at, oh wow, look at the student. Their online test grades are middling, but their midterms are a good match to their online test grades. It's just their homework is dogging the crap out of them. Okay, throw the homework out. That's something I literally do. But again, I don't do it if I see people just aren't doing your homework, because I've learned that when people aren't doing their homework, they fail. And they fail, and it's too late to help them, even if they only make it through the first 3 chapters of the course without doing their homework. They are dead for the rest of the semester. There's almost nothing they can do to recover. Okay.
Are we up to date on the videos for
yes. So I'm up to date in the sense that between what I have on my lab, on my YouTube channel, and in general, then yeah, because every lecture I've ever given for the last 3 years has been up there. So you can find a lecture. Problem is, I don't want you to have to look at 1 hour and 20-minute lectures. And in some cases, they're summer lectures, in which case they're more like 2.5, 3 hours. So in that sense, yes, they're complete, in the sense that I have, a nice little pithy 15, 20-minute problem solving. No, I don't have that.
Okay.
But I'm building it as we go.
All right, because I didn't see a video for last Wednesday.
Okay, gotcha. So let me look. Last week was week 4. And yeah, so I in fact, I put them up as the week's going along. So there are videos up there adding 4 vectors, world's greatest vector addition problem, vector addition part 1, vector addition 4 vector problem. So some of these are actual full scale lectures, and then other ones are just problems I pointed out. So yeah, chapter 5, I'll be filling out today and tomorrow. Chapter 5. Week 5, I should be filling out today and tomorrow, because it starts February 6th. Okay, which is today.
Okay. Also, some students are asking when the midterm would be.
I put the midterm on the syllabus on purpose, because that is the date it's going to be no matter what. So you always got that. Let me pull it up for you real quick, because I know that means you're probably wanting to know. So teaching stuff, I'll go to my folder TCC, I'll go to my folder spring 23, and there it is. And this is the one with the latest date. Yeah, that looks good. No, that looks good. Okay, let me see what happens. All right, I'm trying to pull up the syllabus right quick just to make sure it's in, of course, it's in our helpful documents. I did not put it in the syllabus area of Canvas. When I figure out how to use that in a user-friendly way, I might start that, but until then, nope, not gonna happen. All right, here we go. I look at the schedule and it says my midterm is planned for a Wednesday, 2/29. Let's make sure 2/29 is an actual Wednesday, because that could obviously cause some difficulties. But it's the last Tuesday before the spring break. Or excuse me, maybe it was not Tuesday, it's stupid Wednesday. I don't know why I even said Tuesday. So the 29th does not occur on at all, because it's 30 days to have September, April, June, and November. Except for February, it's got 28, sometimes 29. So it's actually May 1. So May 1 is the day of the midterm. And you will have it at this time period. I will let you start up to 45 minutes early, or I will let you start up to or finish up to 45 minutes late. Is that the day y'all have lab on? Is it Wednesday, or do you have it on Monday?
We have lab on Mondays, and it's looking like May 1st is a Monday.
Oh, wait, did I look at something wrong? Oh. I wasn't sure.
For midterm,
I don't know. I
March.
don't know why I said May.
or March.
Yeah, I probably said May, and that's probably why I said it. But yeah, March 1st is what I'm going for, and that is a Wednesdays, at least according to my calendar for 2023. So yeah, that's what we'll do. So if your lab is on Monday, then that fixes the problem. So you should be able to take the exam that day. And like I said, if you ideally, I'd like you to have the full 2 hours roughly. So you've got an hour and 20-minute class normally from 5:20 to 6:40. But I'd let you start up to, let's say, 40 minutes instead of 45. So you can start up to 40 minutes early or finish up to 40 minutes late. Just try to be prepared to do that. And you've got, let's say, up to 10 days before then, if you can't do it, because I'll have to redesign the exam to make sure it's shorter if I have one person that physically can't do that. Okay, because everybody's got to take it at the same time. Anybody else? Looks like I got a ton of people in here. I got 23 students. Life's going pretty good. Yep. Okay. All right, so let's start solving some problems to get out of chapter 20. Or excuse me, out of chapter 3 and into chapter 4. So first off, I'm going to share my screen with this little hockey puck problem. So you might recognize this. In fact, it's very much like a problem that your textbook had, or excuse me, that your online practice test had. Hopefully it's big enough where y'all can see it. There you go. It says a hockey puck slides off the edge of a table with initial velocity of 20.0 meters per second. The height of the table above the ground is 2.0 meters. What is the magnitude of the velocity of the puck just before it touches the ground? How far from the base of the table does it land? And how long is it in the air? You'll see there is a question sort of like this in your practice test bank, but it's broken up into like 3 different questions. So in fact, you'll get 3 questions about a hockey puck with those exact same numbers, but one's the final velocity, one's how far away, that kind of thing. So that's what I'm doing there. So now let's stop sharing that screen and let's start sharing a different screen, specifically my iPad screen. So start screen, there you go. And of course, it's doing the once a week thing where it requires me to download something that clearly I've downloaded a kabillion times. Okay. And boom, there we are. Okay. So what we have here is a problem, and your coordinate system you use is somewhat arbitrary. For instance, I'm going to imagine the tabletop being like, yes.
Can you share the screen of the
Second.
For the question, you mean?
Yes.
Okay, yeah, let me stop sharing that for a second. If you want to take a screenshot of it, that might help you.
Yeah, that's what I'm trying to do.
Okay.
Thanks. Oh, no, 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 no. Just a second.
Did it work this time?
It did, but I have like a window that was hiding a part of it.
Ah, jerk window. All right, so I'm going to go back to sharing the other way. All right, so going back to my iPad share, my good notes and whatnot. I'm sharing. Okay, so we'll represent that little tabletop with the puck on it by that little black line right there. And then I'm going to say, well, I'm going to make the worst drawing ever of a straight line. Okay. Then I'm going to say straight line this way. Not like that at all. Straight line this way. Okay. Now what's going to happen is we have a puck up here that's moving. So now all of a sudden it wants to draw stuff pretty. It's moving at a velocity of 20.0 meters per second. What it's going to do is fly off and land like that somewhere. What we know is that this height is 2.0 meters from here to here. Okay, so I can arbitrarily make this my y-axis and make this my x-axis. Okay, now what I'm trying to teach you, which is sort of the conceptual idea of physics of projectiles, is that the horizontal motion and the vertical motion are completely separate, but they're integrated in the sense that basically however fast you throw the ball in the upward direction or in the downward direction or with no vertical component whatsoever, those all dictate about how long the object gets to stay in the air. As long as it's in the air, then the horizontal component of velocity, since there is no air resistance, that just stays constant and moves. So for instance, if you're in the air for 4 seconds and the horizontal velocity is 20 meters per second, then you're going to get to land 80 meters away. So in that sense, it's completely separate. So with that in mind, what we've asked for here is how far, how fast it's going just before it touches the ground, how far from the base of the table does it land, and how long is it in the air. So I want to know, let's say D equals question mark. I'm going to up the ante a little bit and say that V final is equal to question mark, and I'm going to put a vector symbol on it, so that makes sense. And I'm going to say T final equals question mark, because that's really what they asked for. Okay. So for starters, this problem, since the puck left off a horizontal table, can anyone tell me what the vertical component of velocity is of the puck initially?
Before it slides off the table, it would be 0.
Exactly. And as soon as it slides off the table, it's going to start speeding up in the downward direction. But initially it has initial velocity of 0. So in fact, its analysis is exactly equivalent to dropping an object, ignoring sort of the diameter and radius of the puck, which is not that bad. But anyways, it's exactly the same as dropping an object from a height h, which is what I'll call this too. Okay. So there's an equation that gives us, for instance, the time that something would be in the air if I knew, for instance, the acceleration, the initial velocity, the initial height, and the final height. Can anybody think of one of those kinematic equations that would come in handy there?
Would it be, I think v squared equals v naught squared plus 2 times the acceleration?
That can actually jump us to getting the velocity. Absolutely. Especially since you're considering the Y motion and you know that the X motion, the velocity is not going to change. But what I'm looking for is one that gives, and that could also be used, by the way, to do the change in positions. But in order to do the change in positions, I'd need to know the initial velocity and the final velocity. So that's the problem with that. Can we think of one that has maybe that can allow us to find out how long it's going to take to land?
X equals X naught plus VT plus 1/2 AT squared.
There you go. And since it's in the Y, there's no sense in, I mean, there's nothing wrong by writing it this way. A sub Y T squared plus V0 sub Y T plus Y0. Okay. So in our problem, since I've drawn our coordinate system, this equation becomes Y is equal to negative 4.90. You know, the units are meters per second every second. T squared. The initial velocity in the Y direction, of course, is 0. And the initial Y0 is actually going to be H. So I'll say plus, H, which is 2.0 meters.
The -4 came from, well, it's half the gravity for Y. Is that right there? Is 1/2 acceleration times Y?
Y is equal to negative 1/2 the acceleration times time squared. So if you take 1/2 of 9.8, you'll get 4.9. That's why that number's there. And notice the 4.9, since it has units of meters per second, that when you multiply that by T squared, that's just going to give you meters. So you can see that the Y does come out in meters like you expect. So I'm now in a position where I can actually say at Y equals 0, which is really the height that the puck should have when it hits the ground, we get the following. 0 is equal to negative 4.90 meters per second every second T squared plus 2.0 meters, or finally we can say T is equal to the plus or minus square root of 2.0 meters divided by 4.90 meters per second and per second. And that, notice the meters cancel out and I end up getting a second squared in the numerator. And in fact, from the physics of this, I set up as positive clearly. Never mind about the plus is positive. I was thinking of the later part of the problem. This is plus or minus. If you happen to notice, you probably will find a T that exactly is the negative of the T for which it lands. And that's basically splitting the parabola up in two, because every one of these equations, when you set them up for projectile motion, it's imagining a projectile starting from ground height, going to a max height, and then setting down. So the negative time corresponds to a time back in history when we could have left or shot the projectile and it would reach the edge of that table at exactly T equals 0, moving at 20 meters per second horizontally. So there is actually some meaning to those negative times, but you rarely have to worry about it. So anyways, I want to take 2 divided by 4.9. And obviously, 2 divided by 4.9. And then I'm going to take the square root of that, which is the 0.5 power, so I can do that quickly. And this gives me 0.63. Now that's technically all the sig figs I'm supposed to have, but I'm going to carry some extras just in case. And that is seconds. So that's how long it's in the air. And we're going to call that T final, like I did in the diagram. So I now know how long it's in the air. Now, additionally, since I told you the motions are completely separate, that time is how much time the puck has to move horizontally at 20 meters per second. So now I can recall the kinematic equation that says, well, let's do it this way. Let's say V bar is equal to X minus X0 over delta T, which we almost always called X minus X0 over T, which means that X is equal to X0 plus V bar T. But in this case, V bar equals V is equal to 20.0 meters per second. Does that make sense to everyone? Oh, yeah, that works. Okay, so now we can get that D is equal to, notice our initial X position was 0 plus, now our velocity is 20.0 meters per second times 0.63888 seconds. Okay, now if I multiply it by 10, it'd be 6.3. So when I multiply it by 20, it's going to be 12.6, maybe 12.7. So we're going to call this 12.7. And that really is giving one extra sig fig already. So I'm going to call that 12.7 meters, and that's equal to D. So I now have solved that problem as well.
Where does 0 come from? Is that the angle?
Okay, so you see that my coordinates has the origin right here. So that means the 0, the position X at time t equals 0 is clearly right there directly above the origin. So the X0 is 0. That when you subscript something with a 0, that's supposed to mean basically, hey, what is X when t equals 0? Well, we pretended we started watching this at the instant the puck left the table. At that instant, you can see that the puck is directly over the origin, therefore X0 is equal to 0. Does that make sense now?
Yep.
Okay. All right. Now, and that's part of the learning part of all this junk is kinematics is not that hard, but you've got to really learn what each of the little things mean in each little problem. And sometimes they can change a little bit. So you got to be prepared for it. The next question we're trying to figure out is what's the final velocity? What I'm going to tell you is this. So I'll draw another coordinate system rather quickly. And I'm going to say the y-axis goes up and the x-axis goes to the right, say, and now I'm going to put that as the x-axis. I'm going to put that as the y-axis. And what we're going to say is that the final velocity V final is what we want to know, but do we know either of these components yet? Do we know the x component or the y component of velocity?
No, we know the X component now.
Yes, we know the x component. So in fact, this right here is 20.0 meters per second. But what we need, and I'm going to find this angle right here, phi equals question mark. What I need is that other velocity, that's V final sub y. This is V final sub x. So does anybody know an equation that relates if I have, for instance, well, I do have time, but time was something I solved for. So what you want to try to do when you're solving a physics problem is ideally use as little things that you calculated yourself in the problem as possible, because if you're actually with someone that's grading your test, and they might not see the fact that you made a mistake on the simple part of finding the time, and they'll see that all the answers thereafter are wrong. So it's better to try to stick to not using those numbers. So if I wanted an equation and I knew that the initial velocity in the y direction was 0, I wanted to know the final velocity in the y direction. And I do happen to know the acceleration and how far it moved. Can anybody think of an equation that I'd want to use to find that final velocity? One of the kinematic equations.
Is that the formula I said earlier, or?
Yep. Yeah, the one you said earlier. I
Okay.
think it was you anyways, where you said basically V final
Yeah.
squared is equal to V0 squared plus 2a. Thank you for the musical entry. Well, x minus x0. Stop that. 0. Okay. So in this case, I'm actually going to subscript everything y. And in fact, I'm going to say, you go away. And I'm going to call this y minus y0. Does anybody recall what our y0 is?
2.
Exactly. So this is 2.0 meters. This a, of course, is negative 9.80 meters per second every second. And the initial velocity in the y direction, does anybody know what that is?
Would be 20.
The x direction velocity was 20, but the y direction, remember this
Negative gravity.
negative gravity is definitely the acceleration, but the velocity, since it launched off a horizontal table, the instant it got off that table, it was not moving
0.
upward or downward. Exactly.
See,
Oh, I got you.
So that's the 0. I think that's what I heard somebody say. So anyways, what we have is that the final velocity in the y direction is equal to, and here's the reason I started to say the plus or minus, 0 plus 2 times negative 9.80 meters per second every second times, now in this case, I'm getting negative 2.0 meters. Okay, so it was a little touch and go. It was a little scary for a second there because we had a negative under the square root, but now you see that it fixed itself. And in fact, we still got to choose, is the y component of the velocity in just before it hits the ground, is that y component of velocity down or up?
Down.
Down. And is down the positive or the negative y direction for me?
Negative.
Yep. So we're going to choose the negative sign, and we're going to say basically the square root of 39.2. And that's meters per second every second times meters, which would be meters squared per second per second. So remember, I told you mathematically, meters per second every second is the same thing as meters per second squared. So this is a good time for you to realize it's meters squared per second squared, because when you take the square root of it, it gives you exactly what you want, a negative meters per second. So I'm going to take the square root of this, and I get 6.261. Actually, I'm going to say 6.2610. Now that's meters per second, and that's in the downward direction. That means this right here is about 6.26, and that up there is about 20. So we got what we need, but really I need to pay attention a little bit here. when I multiplied 9.8 times 2 times 2.0, I really only had 2 sig figs. So this 2 is not fair right there. And in fact, when I took the square root, I was only allowed to keep 2 sig figs. So technically I can only round that to 6.2. But anyways, that's not that big a deal. The main thing is I need to figure out what is V final. So V final is going to be the square root of 6.2610 meters per second. And in fact, each of those guys are non-significant figures, plus 20.0 meters per second quantity squared again. And then I take the square root of that. Now here's the weird part. When I take the square of 6.26, I get 39.2-ish, which remember was basically just 2 sig figs. It ends at the, in other words, this part right here. Let me give myself a little bit of space. This part right here is 39.2, but that 2 is not a sig fig. This part right here is 400.0, but notice I used all my sig figs and just getting to 400. So my rounding place is supposed to be to 1 decimal place. So if I add 400 to 39.2, I get 439.2, but that 0.2 is not significant. But luckily, since it's 429, I'm back to 3 sig figs. So I can take the square root of that, and I'll get that the final velocity's magnitude is 20.9. Since it's a 5, I usually write the next digit as well. So 5.7 meters per second. And then phi is actually the inverse tangent of the opposite over adjacent, which is 6.261 over 20.0. Now, obviously, I only had 2 sig figs, so I'm really only supposed to round this to 2 sig figs. So I'm going to hit arctan of 6.261 divided by 20. And that gives me 17.38 degrees. That's only supposed to be 3 sig figs. I mean, 2 sig figs. So I have to call it that. So my final velocity, VF, is equal to basically I can call this 21.0 meters per second at, notice I measured that phi clockwise, in other words, downward from the positive x-axis. So I can just call this a negative 17 degrees. And I don't have to do any other specification, because when you put a negative, everybody assumes it's clockwise from the positive x-axis. When you put a positive, everybody assumes it's counterclockwise from the positive x-axis. And I have the drawings to show that I was dealing with a positive x-axis, so that all works. So that's a typical projectile motion problem. And what I was trying to do here was make sure you had a projectile motion problem that was not launched and landed on the exact same level. Those are sort of the chucker problems. In fact, we give those problems in our 201 course. Okay. And I've derived all those formulas for you for the max range, the max height, the time in the air, the final velocity. I've done those things in symbolic form. You can see them all over my YouTube channel, but really you should try that one time using, values like V0 is the initial velocity, theta is the angle above the horizon you shot it at, and then calculate things like how long it's going to be in the air in terms of those symbols, how high it's going to reach at its max point, how Well, I already said how what the final velocity is. Those are things that formulas that you can use. And if you ever took the time to derive them, you'd probably have them memorized whether you meant to or not. So anybody have any questions on that particular problem?
You should be able to calculate that negative, shouldn't you?
Yes, if I would have used
Because I
instead
see
of
you dropped the
using-
negative when you did arctangent.
Oh, right. So I could have, but I never trust trig functions or inverse trig functions to deal with sines correctly. There's too many variables. If you're a computer programmer, you know, for instance, that the little file, the mathematical file that C and C++ comes with allows you a proper inverse tangent, inverse cosine, cosine, and all that stuff, where you can put in the negative numbers and it knows just what it is. But if I put in the inverse tangent of a negative number, it doesn't know whether the opposite or the adjacent is the negative. So it could blindly spit out a negative, which in this case would be okay, but it'll also do it when it's not supposed to be. So what I do is always keep my wits about me, never put in a negative sign in my trig functions. Okay. That's just something I found way more useful, because it turns out if you always use the angle sort of closest to the axis, the nearest axis, then you can use your physics to make sense of whether it's positive or negative. Another thing, which is what I thought you were asking, is if I would have used V is equal to V0 plus AT, that would have naturally given me the negative Y component of velocity. So, but the reason I told you I didn't use that was because I have to use the time, which was a calculated quantity, and it's best not to use that if you don't have to.
Okay, thanks.
No problem. Good point though. All right. All right. So let's do another screen share so you can see another problem. I'm going to share screen with this one this time. You might want to take a screenshot of it. So this one says a child throws a ball with an initial speed of 8 meters per second at an angle of 40 degrees above the horizontal. The ball leaves her hand 1 meter above the ground. How long is the ball in flight before it hits the ground? Okay, let me draw this on my pad real quick, and then I will share it with you. So first off, I'm trying to write in black, but it does not want me to. Okay, so now I'm going to draw my coordinate system. And now I'm going to draw my coordinate system this way. Okay. So I'm just sort of drawing a coordinate system right now, X and Y, and I'm realizing that the actual throw starts from a height of 1 meter above. So I chose to put my coordinate actually at ground level. Now I'm drawing some things to show what the actual velocity the child is throwing at is. So V0 is equal to 8.00 meters per second. And it's at an angle of 40.0 degrees above the horizontal. So I'm going to say that the projectile is going to do something like this. Again, I'm writing it down, and I know I'm not sharing it with you, but what they're wanting to know is T final. And what I'm going to ask you is T final, and let's say V max, and maybe even V final. In other words, these are all things that you could actually ask for when solving such a problem. So now that I've gotten the information down that I need, which is pretty much 8 meters per second, angle 40 degrees above the horizontal, and the ball leaves her hand 1 meter above the ground. How long is the ball in flight before it hits the ground? So I've done all that. And I've drawn a diagram, and in drawing the diagram, I've included that information in it. So I can now share it with you. And you can see, for instance, how I'm going to now solve this problem. So immediately I realize I've got some equations for kinematics, and those are going to come in super useful. So my solution is going to start right here. One thing I know is that y as a function of time is going to equal negative 4.90 meters per second every second times t squared. Now, also, I can see that V0 sub x is 8 times cosine 40, which gives me 6.128, which is 1284, say. That's giving me 2 extra sig figs. That's meters per second. And V0y would be 8 times sine of 40. And that's going to be 5.1423. And that's 2 extra sig figs as well. So that's just some data that can come in handy. I know my kinematic equation, and actually this started off ugly, so I'm going to erase it. I'm kind of angry with that. So anyways, my y is going to equal negative 4.90 meters per second every second times t squared. Now my initial velocity was actually upward in the y direction, so I'm going to say plus 5.1423 meters per second t plus 1.00 meters. That is my y as a function of time. Okay. Now, additionally, my x as a function of time is just going to be equal to my x component of velocity, which is again positive. In this case, it's 6.1284 meters per second times time. That gives me exactly the position x at any time up until the TF, which is what they're trying to find out. So what I'm going to do is I am going to try to figure out what t gives me y equals 0. So for TF, I don't know why I switched to curves all of a sudden. I will solve for y equals 0. Okay. Now what that means is I put a 0 here and it gets negative 4.90. I've already done my unit stuff, so I'm just going to drop that off right now. Plus 5.1242, or excuse me, 1423. Again, that's extra sig figs there, times t plus 1.00, like that. Okay. So in this case, you might as well use the quadratic formula, which basically says t is equal to negative of 5.1423 plus or minus the square root of 5.1423 squared minus 4 times negative 4.9048, and then c, of course, is 1.00. All that divided by 2a which would be negative 9.80. Okay. So this is one of those things where I can watch this. I'm definitely going to have negative 5.1423 plus or minus. Now I need a square root of 5.1423 squared. And remember, that's only 3 sig figs, so that's only supposed to be 26.4. I'll say 43 is extra digits. Plus the other one's supposed to be, in this case, it's an actual positive because a negative times a negative. So I'm going to say 4 times 4.9 times 1. Oh, 4 times 4.9. That gives me 19.6. And of course, that has 3 sig figs. So that actually works out okay to 19.6. There's zeros after it. That's why I'm not putting them. And then all this would be divided by negative 9.80. Okay. If you wanted to analyze the units, you'd see that works. But what we see is in both cases, we get the tens place under the square root. So I'm going to write negative 5.14, again, 23. Now I can put back those units just to make sure things work right. I'm going to say that's meters per second. Plus or minus the square root of 19.6 plus 26.44324.929. I'm just carrying all the digits just for the heck of it. That's the square root of 46.0432. That's more than enough extra digits there. Notice that came out to meters per second times meters. So this is meters squared per second squared. Times, let's see what else. Wait a second. That was meters squared per second squared minus 4.
Sorry,
Yes.
Professor, did you solve for X to get, I mean, you solve for T, like you separated the equation to get T, right?
Yeah, I used the quadratic formula, but yes. So in other words, you don't want to take any time trying to factor it because clearly you're not going to have any easy trick at factoring it when the coefficients aren't whole numbers. So now if I take the square root of that, so 0.5, I'm going to get, here it is, negative 5.1423 meters per second plus or minus 6.78. Now remember, this was actually 3 sig figs in there, so the 7/8's fine, but I have a 5 and a 5 here that are extra. Those will be meters per second. And then I'm dividing that by a negative 9.80 meters per second squared. Now, the whole reason I took this time to write everything out is so I could trace the sig figs, which I really don't care that much about, but I want to make sure y'all know what the rules are. So if you look here, I'm going to add a 5.14 to two decimal places and a 6.78 to 2 decimal places. I'm possibly going to add them or subtract them. Notice that the negative 5 is actually less negative than the 6. So if I did a negative 5 and the bottom symbol negative 6, I get like a negative 11. And then I divide that by a negative number, I'd get a positive. So that works okay. So the bottom sign definitely gives us a positive time. I'll mention that by putting a little circle around it. Now the plus time, I'd have a negative 5 plus a positive 6 something. So clearly that's going to come out to be positive, and then dividing it by a negative number is going to give it a negative. So I really can only use the bottom number or the bottom symbol, which is minus. So I'm going to say negative 5.1423 minus 6.7855. That's equal to negative 11.9278. Again, 1 sig fig, or excuse me, 2 decimal places was all I had, and that's meters per second over negative 9.80 meters per second, which I'm writing like that. So we'll see how it works out. I'm going to divide that 11 blah, blah, blah by 9.8. And I get 1.21. That's 4 sig figs divided by 3. So 1.21 is all the sig figs I'm allowed. I'll put the extra 7 there, and that's actually seconds. So TF should be about 1.217 seconds. That's how long it's in the air. That was one of the questions we were asked. That was the only question, really, the problem I gave asked. But I said, hey, we should be able to do other problems too. So let's, for instance, figure out what is the max height. Well, if I took and tried to find velocity in the y direction as a function of time, I'd know that's just dy dt, right? So if I took that derivative, I would get Vy of t is equal to negative 9.80 meters per second every second times t plus 5.1423. Again, remembering that the 23 is not significant. So in order to find out at what time the thing reaches its max height, all I got to do is set the y velocity equal to 0. So I can now say at t, call it max slash t1/2 flight. Well, actually, I can't even say it's t1/2 flight because that's technically no longer true. But at t max implies Vy of t has got to equal 0, because if it was a positive number, then it still needs to decrease a little bit because it's going to continue to climb up. If it's a negative number, then it's came from a spot higher at which its velocity was lower. So I have to set it to 0. And in doing so, that gives me 0 is equal to negative 9.8. We've already worked out the details on the units, plus 5.1423. Again, already worked out the details on the units. So I get t is equal to 5.1423 meters per second divided by 9.80 meters per second every second. So that's just going to give me seconds. So let me take this 5.1423 and divide that by 9.8. And that gives me 0.5247, 0.5247. That should be 3 sig figs divided by 3 sig figs. So I'm going to say 7.2 seconds. So that's the time when it gets right here at this spot. That's t equals 0.5247 seconds. Okay, so now if I actually plug that into my y value, I will have the height. So y max is equal to y of 0.52472 seconds, which is equal to negative 4.90. We've already worked out the details on the units, as I said. I'm just going to put 0.52472, and I shouldn't even put the units there. I'll put squared plus 5.1423 times 0.52472 and then plus 1.00 meters. When I do that, negative 4.9 times 0.52472. Now I'm going to square that. And that's going to be added to 5.1423 times 0.052472. Okay. So when I did the 4.9 times the 5.2472, we had decided that only the 7 and 2 were bad. So it's 3 sig figs times 3 sig figs. That would have gave me 2 decimal places. So in other words, this number had 2 decimal places, keeping track of that. This number, however, is 5.1423 times 0.052472. That's supposed to be 3 sig figs times 3 sig figs. So that actually gives me 3 decimal places. So we're really only allowed to round to 2 decimal places, and that's consistent with this. So anyways, I'm going to take, it looks like I'm still negative. How am I still negative? 0.542. So let's check again. Negative 4.9 times 0.52472 squared. That gives me negative 1.34. I'm just going to write these down. Negative 1. In case I made some kind of careless arithmetic mistake or something. 3491. So that's extra units there. Plus 5.1423 times 0.52472. That gave me, yeah, that's what I was thinking. Okay, so that gave me 2.69. And then let's take a couple extra digits. I'm gonna call that 83. Okay, and then plus 1. So everything should get 2 decimal places here. So I can say Y max is ultimately equal to, when I add these together, I get plus 1.00 plus negative 1.34912. I get 2.34. And I can carry an extra digit 91. Carry 2 extra digits, meters. So my Y max should be 2.35 meters roughly. Any questions on that one? Now I think you can figure out how to do the V final. Obviously, the way that gives you the right sign would be V is equal to V0 plus AT, but that requires us to use the T that we calculated, but that's fine. What you're ultimately going to get, of course, is a velocity that has an X component, which we decided was 5.1423 meters per second. And then you're going to get a Y component that you need as well. And of course, you'll need that angle phi. So if I wanted to find out what that V0y is, I'm just going to say the initial velocity V0 was positive 5 point, whoa. Oops. Let's hope I didn't do this errantly in some of the other work. Notice I just copied this 5 point here. That's my X component, when in fact that was actually my Y component. My X component was 6.1284. So 6.1284 meters per second there. So that's the one that didn't change. The V0y is going to be 5.1423. I think that's what I had. Yeah, 23 meters per second. So if I take that and subtract from it 9.8, so 5.1423 minus 9.8 times point, I got to use my time now, 52472. That gives me V final is 4 point, oh, that's a really small number. It's barely, it's 0.0000044 meters per second. So you can see it's really teeny. And in fact, the vast majority of the velocity is really just the horizontal. So you can say that basically V final, at least to the proper number sig figs, is essentially 6.13 meters per second. And it's, you know, slightly below horizontal. In other words, because the kid didn't throw it that fast, it was really a low angle. So any questions on that one? And again, I've neglected to turn up my chats over here. So let me put them up.
Why is V final 6.13 when you had it as the 0.00044 meters per second?
If you take the square of 6.1284 and add that to the square of 0.000044, that doesn't, the VF squared does not register within the sig figs of 6.12 squared. Because 6.1243, or excuse me, 1284, when I square that, I only get 3 sig figs. That comes to the 10th place. However, when I square 4.4 e to the negative 5, which is what it gave me for the final velocity, that gives me a 0 followed by a decimal point, followed by 9 zeros, and then a 196. So in other words, there's no meaningful way for you to take into account in a consistent way. There's no meaningful way to take into account the horizontal component of velocities, because it's so small that it doesn't even align with the error that you have in any part of it. So really, it's essentially a round off error.
Thank you.
I'm sorry to be.
Could you write how you calculated that? Because I'm not following that. How you
Okay,
got
yeah.
that?
Let me do that for you real quick. It's not a biggie. Okay, so let's turn to the next page. And what I'm going to do is I'm going to say V final is actually equal to the square root of 6.1284 meters per second squared plus 4.4 times 10 to the negative fifth meters per second squared. That's going to equal square root. Now, when I squared this 6.1284, I got 37.55728.656. Now, according to the sig fig rules, I only had 3 sig figs, so all of these guys are insignificant. Now, when I square this guy, that wasn't supposed to be an equals, that was supposed to be a plus. Okay. When I square this guy, 4.4 e to the negative fifth squared, I get 0.00000000193 meters squared per second squared. So, and that's all the sig figs. So that matches up down until we get to 6, 7, 8, 9 decimal places. So basically 1, 2, 3, 4, 5, 6, 7, 8. Right here is where the 1 is, then the 9, and then the 3 when I go to add them. So I'm adding them to meaningless digits. So ultimately, I'll get the square root of 37.55728656193. And basically all these digits right here are insignificant. Does that make sense now?
Yes, thank you.
No problem. So that's ultimately what happened to the velocity. We've still got a little bit of time. Let's try this guy. A swimmer wants to cross a river from point A to point B as shown in the figure. So this is actually a kind of neat problem. Let me draw it really quickly. You've probably seen something like it in your homework. This is 240.0 meters. This is going to be 180 meters, which I'm going to call 180.0 meters. And this is point A. This is point C. And this is point B. And we've got a velocity of the river equal to 5 kilometers per hour. Now, what we do know is that the swimmer is going to be swimming with a velocity u sub s at 45 degrees, which I'll call 45.0 degrees, just to make sure we have a lot of sig figs. And what we want to know is what must u sub s be to get it to end up at B. So US equals question mark for swimmer reaching B. In other words, just going along that line. So what I did was I used the idea that velocity is equal to distance divided by time. By time, to realize that time is actually distance divided by velocity. So if I look at just the A to C part, so here's our solution. If I look at just the A to C part, and we're not going to C, but notice I've got the swimmer has to swim enough that he goes the distance 240 meters in the necessary time. So we're going to find out what that time is. So time is going to be, stopping that, I'm going to say time is in fact the distance, which is, let's call this D1. And let's call this D2. So this is going to be D1 over U sub S times the cosine of theta, which is what we're going to call that angle. Okay. I can plug these in later, but that the important thing is that. Okay. Now, in going from C to B, what you got to realize is that the velocity is in fact it's in fact V river minus U sub S times sine theta. Okay, so that's how fast it's going. So that means this time would of course be D2 over V sub R minus U sub S sine theta. Well, we need those two times equal to each other. So we can say D1 over U sub S sine theta is equal to D2 over V sub R minus U sub S. I wrote that was supposed to be cosine over here. Hold on a second. Cosine theta, and this one will be sine theta. Now this looks like a mess, but it's actually really quite nice. You can say D1 times VR, the velocity of the river, minus D1 times U sub S times the sine of theta is equal to D2 times U sub S times the cosine of theta. Now we can get the U sub S terms together, and I can say U sub S is equal to D2 cosine theta plus D1 sine theta. And then that all, of course, is equal to D1 VR. So I ultimately figure out that US is D1 times the velocity of the river divided by D2 cosine 45 plus D1 sine 45. And all you have to do is put in your D1 and D2, and we have the actual velocity. Okay. Remember D1, of course, is 240. And D2, of course, is 180. Okay. And of course, V river is 5.0 kilometers per hour, which you can convert to meters per second if you want, or you can just leave it all in kilometers per second. So that's it. It's 6:40. We're done with that problem. I've done, I think, more than enough examples for chapter 3. We'll jump into chapter 4, Newton's laws of motion. I'd highly recommend you read some information about the history of Isaac Newton. It's kind of interesting. James Gleick wrote a very nice biography of Newton, and it was only like this thin. So that's kind of neat. But you guys are free to go. I will wait for the last person in case anybody has any questions. And this video should be posted sometime tonight. I think I might try to put those numbers in right quick. Let's see, D1 was supposed to be 240.
You
Yes.
mind sharing the last problem, like the
Yes. Yeah, I can do
problem
that.
itself? Okay.
Oh, the actual question. Okay. You should see that now, right, swimmer?
Give me a second. Take a picture. You mind resharing the hockey the hockey one too?
No, not at all. Here it is. Nope, not that one. There it is.
Thanks.
No problem.
Oh, hey, Professor.
Yes.
I have one question.
Mhm.
Going back to the beginning of the year where I asked you about an experiment. Do you know if there's like any like how do I say any like properties in physics that you were surprised that there's no relationship in between? Like
Uh,
I
well,
have my
sort of.
possible experiment topic was finding the relationship between and the frequency of a wave, and I was wondering if that's like, do they have any relationship? Because I
Yeah,
know
so like the frequency of a wave or the period of the pendulum, for instance, does not depend on the mass. That's an oddity for me. You know, I can understand by doing a derivation that it turns out to only be related to the length of the pendulum and gravitational acceleration. But it doesn't make any sense to me that it actually turns out to be independent of mass. So that's one thing. Another thing might be yeah, nothing really jumps out at me. The velocity of a wave doesn't depend on the height. That's kind of neat. The frequency of the wave or the period of the wave is not related. Well, it is related to the wavelength in a very specific way, but that sometimes surprises you how that way works. But that's just about it as far as the things that really surprised me, at least in terms of things I can think of right now.
I get you. I'm just
Sorry
ready
about
to,
that.
it's all
I'll
right.
think a little bit more about it and see what happens.
I'm just trying to get some topic on because I've studied waves a little bit, but I'm trying to like wait until I understand a few topics and then pick do some
Now
experiments.
there is an area of when you're actually studying like ocean waves. There's a near field and a far field and all this weird kind of stuff. It turns out that waves that are just waves, not the ones that break. Once they break, that's an odd phenomenon that as a result of usually, at least most of the shore breaks are a result of the depth getting to be too large of a fraction of the height of the wave. That causes the velocity of the lower part of the wave to slow down, while the upper part of the wave, which is only attached to the lower part by surface tension, so that it actually slings the top part of the wave over the top. And that's what crashing is, or for instance, a closeout, or when you're riding inside a tube if you're surfing. All that stuff is kind of neat in that the speed relates to the depth of the ocean, at least when you get close, where the depth is comparable to the actual height of the wave.
So just now thinking of something after listening to the ideas, um, is there a relationship between the wave period and the wave height, or is there no relationship at all?
No relationship that we know of for common waves. There are other waves in nature that may or may not be the same way. Like we sometimes call the function in quantum mechanics a wave equation or a wave function. In that case, there's weird things that the actual amplitude can depend on. But that's those are kind of weird.
So there is no relationship between the wavelength and the wave height.
Right.
And if I wanted to do an experiment, because that actually sounds pretty interesting. But now thinking about it, I'm kind of surprised by it, because if the amplitude increases, wouldn't that mean that the period theoretically kind of would last longer, correct? Or am I thinking it incorrectly?
Right. And I see why you'd think that, because obviously, you know, you see small waves get knocked down all the time. Big wave might not get knocked down. But yeah, what you want to do a search for is, and it's kind of hard to do it, but capillary waves versus gravity waves. And that's the two ocean waves that exist. Basically, the capillary waves are due to basically wind flying over the ocean, causing a capillary effect that causes the little ripples that you see on top of the wave. And then the gravity wave basically just forces the fact that gravity pulls slightly forward and slightly backward over a large area. You know, gravity pulls sort of this way and this way if you're over a large enough chunk of earth. Or you can think of it as gravity weakens at the top part of the wave and strengthens at the bottom part of the wave, little stuff like that. But I suspect you're going to run into a lot of mathematical difficulties working out the details of that. By the way, I got 4.04 kilometers per hour for the swimmer's speed on that last problem. Anything else, Christian?
No, sir, thank you for answering my question.
All right, have a good one, bud. Bye-bye. Okay, one more screen share, because I did plug in the numbers. And when I plugged in the numbers for the final velocity in the red over here, notice how the meters can sort of all cancel out and it will just come out in kilometers per hour. So I put in the D1 being 240 and the D2 being 180. And if I did that consistently correctly, which it looks like I probably did, then 4.04 kilometers per hour is the swimmer's necessary velocity, which is actually pretty good. But anyways, I hope that helped. Bye-bye. See ya.